cluster level inference.
All right, great, thank you. Thank you all for coming. So today we're going to talk about activation mapping, and this might look familiar to a lot of you. This is a face localizer scan, basically showing people a bunch of faces, a bunch of places, and doing a contrast. And this pretty robustly activates the fusiform face area. But sometimes we get these other areas of activation as well, and we're not sure whether these are real in the sense of, are they actually related to face-related processing, or are they something else? And if there's something else, something that's unrelated, we might call this a type 1 error, a false positive. So in this case, a doctor is telling someone who's biologically male that they're pregnant. So this is a very important type of error that we as scientists try to reduce. And that's because we often might think that findings that we have are real, even if they're not actually real. We have this confirmation bias that makes us try to use these findings as actual physical things when they might actually just be type 1 errors. And a landmark paper by Eklund and colleagues showed that a lot of our inferences in fMRI might actually have inflated rates of false positives. And this is a very important paper. This is just showing us that a lot of the assumptions that we might make as scientists in fMRI may bear some reconsideration. But there's another type of error rate as well, the type 2 error. In this case, a doctor is telling someone who is visibly pregnant that they are not pregnant. And this is also a problem. So a valid method or an accurate method often is defined as something that has low rates of type 1 and type 2 error. You might have certain reasons for wanting to reduce one or the other. So you might have a case where you're trying to find a life-threatening illness. You're trying to detect that in people, and you might be willing to tolerate some type 1 errors. But there's always, often there's a reason to consider both of these at the same time. So today I'm going to look at the false negative rate in cluster-based inference. And often you're going to hear me refer to this as the true positive rate, which is 1 minus that type 2 error. So let's talk a little bit about cluster-based inference for those of you who are a little less familiar. And I'm just going to try to give you a very high-level intuition for this. So let's say that this is a group contrast image. These are voxels with p-values, or let's say even t-statistics at each voxel. And we might want to do a multiple comparison correction that treats every single voxel as independent. Let's say like a standard Bonferroni correction. However, images can be on the order of hundreds of thousands of voxels. So doing a test like that, when there's actually some dependence in the image, when voxels might be similar to nearby voxels, can actually be very over-conservative in this case. So cluster-based inferences were developed to take advantage of this dependence between surrounding voxels. So we might start with a voxel level threshold, in this case a p-value threshold, and I'm going to set it here at 0.01. And then we apply a cluster level threshold. That's the amount of contiguous voxels that are all next to each other. So right now I'm letting everything through. If I let 4 through, you can see the individual voxels disappear. 6, and then 9, we just have a couple large clusters left. And let's reset this image and choose a higher p-value threshold. You can see already the clusters are smaller, and as I increase the cluster size threshold, we lose clusters really quickly until the highest threshold, we have nothing left. So this is just to give you an intuition about how increasing both of these types of thresholds can reduce the rate that a cluster might survive just by chance. I'm just going to reset this. And let's say we know the ground truth, that there is an effect in these areas and there's no effect in these areas. This top left situation would be called a true positive, false negative, true negative, and a false positive. So typically we try to reduce those false positives, and today I'm going to show a little bit about what we know about the true positive rate. The way this is typically done is people will set a voxel level threshold a priori, and then typically we'll estimate a cluster level that corresponds with a desired false positive rate. As Eklund and colleagues showed, often this is done using parametric methods, and that sometimes can be inaccurate. Non-parametric methods tend to accurately control the false positive rate, and here, whenever I say false positive rate in this context, I'm going to be referring to the family-wise error rate, which is the rate of at least one false positive. All right, so I'm going to talk a little bit about my work that's in revision right now. And I'm going to briefly skim through this slide, but feel free to ask questions afterwards. So I'm starting with the Human Connectome Project dataset, and this is similar to the procedure of Creamers and colleagues, and actually some other people are also using this procedure to assess for true positives. So I start with the Human Connectome Project dataset. I'm using 5 tasks here with about 480 subjects. I'll calculate a ground truth map using all the subjects, and then I randomly, for 1,000 repetitions, I randomly sample 20 subjects, do cluster correction, and for the surviving clusters, I compare that to the ground truth map. And so I have that for the 5 tasks, the standard correction that I showed you earlier, and I'll also do TFCE. For those of you who are not familiar, you can just think of this as a way of incorporating both information about the cluster height and the cluster width. And here are some results. These are just the ground truth results. So this is what the map of effect size at each voxel for the social task. And here's a histogram of those effect sizes. And I'm going to highlight throughout this talk areas between large and negative large, so a Cohen's d of 0.8 and negative 0.8. And you can see for the social task, actually 81% of effects lie in this region. And this is pretty similar actually across tasks, where about 90% of effect sizes are large. Also, a side note, you can also see that these effects tend to be distributed, which is a little bit different than the way that we typically think of clusters. But now that we know that most effect sizes tend to be large in these full data sets, I'm going to show what the true positive rate is by effect size. So here's a map where I'm plotting the proportion of voxels, same as the previous in orange, and then the true positive rate in blue. And here I'm showing you the true positive rate at a large and negative large effect size. So for the social task, which is what I'm showing here, the true positive rate tends to be 10% at a large effect size, which is a kind of big deal because if we were doing just a single region analysis where we didn't have to do any control for multiple comparisons, using this one-sided test, we'd achieve a true positive rate of about 96%. So we're going from 96% without any correction, if we were just doing a single region, to 10%. And that's quite a loss of power, especially for a large effect size, especially given that most effects are below this region. So now I'm going to show you across different tasks. And on average, we tend to be able to detect effects less than 10% at a large effect size. Now I'll show you what happens when we go to TFCE. Let me see if I can go backwards. Yeah, there we go. So when we use TFCE, we actually tend to double the effect size. You can see most of these distributions are shifting upwards. There's also a really interesting point that these distributions tend to shift. And I have a couple thoughts about that if anybody wants to talk afterwards. So we get 2 times sensitivity with TFCE. So I was also interested in the spatial distribution of the bias in detecting the true positive rate. So specifically here, I'm going to show for a given true positive rate, whether certain areas tend to detect true positives more or less. And what this specifically is the residuals of this blue plot. All right, so for the standard approach, we actually start to see some bias in these posterior areas where we tend to detect more effects than otherwise. And actually for TFCE, even though we have 2 times the detection on average at a large effect size, there's even more spatial bias in these posterior areas. So it's just a good thing to keep in mind, even though we're able to make an increase in one domain, but we're actually sacrificing something in the other domain. All right, so in conclusion, what have we learned about the sensitivity of cluster-based inference? We find that even large effects that would be detected 96% of the time are typically detected less than 10% of the time after we do a correction in this way. And I'm just wondering whether this is acceptable or whether we should begin to revise our practices. This is important because most effects in the ground truth data set, with some caveats that this is an estimation from 480, not millions of subjects, but 480 subjects, are less than large. And we also find a spatial bias in the true positive rate. So there are many ways that we could go about improving sensitivity. In fact, this is not a new problem across scientific fields. There have been challenges in improving power. And in fMRI, people have given this a lot of thought as well. And here are just a few. I'm just going to go through this slide really quick. We could work within the system, use measures that we're already familiar with, and kind of try to rethink them a bit. So we could do things like relax the threshold of errors that we allow, but we should be careful about these. There's a great recent discussion by Benjamin and colleagues. We could constrain tests to only a set of ROIs, etc. We could also redefine our measures. So I think a measure proposed by Creamers and colleagues is very interesting. It's a ratio between the type 1 and type 2 error rate, and that could be a very interesting way forward. We could also use something like TFCE, or in AFNI, there's a very similar approach called equitable thresholding and clustering. However, just bearing in mind that it might be important to adjust for this spatial bias. All right, so I'd like to thank my lab, especially my PhD advisor, Todd Constable, and my postdoc advisor, Dustin Chinos. I'm starting my postdoc just now. HCP, of course, and my sources of funding. All right, thank you guys.
Thank you, Kurt.